Hello all. Today we are going to discuss few more applications of finite state machines. In our previous lecture we have seen that how addition can be performed using finite state machine, which will reduce the area, and the delay would be very similar to a ripple carry adder. And also we have seen another concept in our previous lecture of pipelining, where throughput can be increased with sequential circuits. Today we are trying to see the similar applications of finite state machines in other arithmetic circuits like multiplication, division, and then we'll generalize it as a iterative circuits. So multiplication we have seen multiple times during this whole course, in module 1 and in module 3, and now we are again taking this concept of multiplication, and this slide is again is taken from module 3 slide. So we have seen that multiplication is a two-step process. In step 1, multiplicand is multiplied with each bit of multiplier, and partial product is generated, and then we are adding the partial products. So this is the example. For example, this is the multiplicand, this is multiplier. Each time we are multiplying one bit of the multiplier with multiplicand and generating a partial product, and then we are adding all these partial products. So in this lecture we are trying to design that what would be the hardware. So let us look at this multiplication more carefully. So what you will see that every time we are adding, first time when we are adding, then we are adding the multiplicand, we are putting the multiplicand here. And what is the condition of putting multiplicand here? When least significant bit of the multiplier is 1. If it is 1, then we will put as such whatever is the multiplicand as the result. Now when next time we are adding, then we are looking at the, instead of 0th bit we are looking at the first bit. Okay, so if it is 0, then this whole multiplicand is shifted left, and then addition is performed. And for the second bit it is again shifted left, and then addition is performed. And for the third bit again it is shifted one more times, then addition is performed. So in other way, so every time this is supposed to be an 8-bit addition, and after adding one multiplicand, one set of multiplicand, then after one partial product, then another partial product would be added, and finally if we consider our partial result as a 8-bit result, then every time we are adding the shifted multiplicand. Okay, so this also we have seen that if my multiplicand is n bit, multiplier is m bit, the result is going to be n plus m bit. Now this hardware cost we have seen last time, so we are trying to revisit in case of sequential multipliers. Okay, so in our previous case we have seen the multiplication when we did this multiplication in module 3. We did this multiplication either using n number of adders, or we have also done using carry save adders, where we are trying to add all these partial products at once. So now let's look at the other method, where if we have a single adder and then we would like to multiply. So if that is so and let's consider n bit multiplicand and m bit multiplier. So if multiplier is m bit, then the total number of steps are going to be m steps. Each step we can map to one clock cycle, or each step we can map to one state of the FSM, finite state machine. Now what would happen in each state? First step or first state, it would assume the result is 0, and it will add the multiplicand to the result. Result is initially result was initialized to 0, so we are adding multiplicand to the result. If multiplier, 0th bit of the multiplier is 1, and in all forthcoming steps every time what we are essentially doing, we are shifting our multiplicand by left essentially we are multiplying it by 2, and we are right shifting the multiplier. So right shifting the multiplier means that this multiplier 0 bit will go away and the first bit will become 0th bit. So this way, in any ith step, we are looking at the ith bit of the multiplier, and by shifting multiplicand right, we are every time we are shifting it by right means we are doing this operation. So we are shifting all the this multiplicand in the right direction. Okay, so these are the two operations which we are always doing. We are always shifting the multiplicand by 1, or basically shifting left by 1 bit, and we are also shifting right. We are shifting multiplier in right direction again by 1 bit. So these two steps we are always doing. The other step is we have to add the result of multiplicand and multiplier if multiplicand and the previous result, if my multiplier 0th bit of multiplier is 1. If 0th bit of multiplier is not 1, then we need not to add. Or in other words, even if we add, we will not show it as a result. So and after this m steps we would be done, because we would have done already these m partial additions. So after m steps we are done. Now if we want to implement this structure, so we can see that we can design this as a m state finite state machine with m states, where each of the state m state will have like your first state will initialize the results, and after that every time the input to this finite state machine is going to be multiplier, 0th bit of multiplier, and there are couple of operations which we need to perform in each of the state. For example, shift left of the multiplicand, shift right of the multiplier, and we have to see whether we need to add or not, and also we have to see whether we have to write the result in our result register or not. So if we see, these are the outputs which we have to generate every time, whether we need to shift right the multiplier, whether we have to shift left our multiplicand, and whether we need to add this operation or not. So whether we need to do addition or not, and whether result register need to be written or not. And the input is definitely multiplier, 0th bit of multiplier, and it's going to be a m state machines, and where the states are simply going from one to another, S1 to S2, S2 to S3, S3 to S4. So essentially it's a counter, it's a modulo m counter. And if it is a modulo m counter, and for example if number of bits is 32, then a 5-bit counter would be sufficient. And so let's look at the data path. So what is data path? Data path is essentially when we are doing multiplication, there are going to be two major portions. One is this finite state machine, which is our control, and which would be determining when to do these operations. And the other part is the flow of operations, flow of data. And because this flow of data would also require some sort of operations like addition here and shift register here. So all of these things will form the data path. So usually data path would have a certain combinational logic like addition, multiplication, and also data path also involve the registers, different kind of registers. And now to control what operations need to be performed and when to perform these operations, and what would be the control bits of multiplexers, all of these things would be decided by a finite state machine, and each state may generate certain output bits, and based on that the operation will work. So here we will see that initially this multiplicand would be stored in the right half. So basically this portion, multiplicand is we have to remember that multiplicand is 32 bit, and in a 32-bit multiplication we will have a multiplicand which is 32-bit, multiplier which is also 32-bit, and the product we are assuming is a 64-bit. Now since 32-bit multiplicand is there, initially it would be in the lower half. Okay, lower half means you can say 0 to 31 bits. Okay, and then multiplier is also stored in the 32-bit register. So every time, and there is also a product register which is of 64-bit wide. Now initially at time equal to 0, or in the starting of my 0th state, I'll initialize this product to 0. So because product is 0, this product 0 would be sent as one of the input to my addition circuitry, and this 32-bit multiplier would be given as the other input. Now based on what is the 0th bit of this multiplier, based on the 0th bit of this multiplier we will add, or based on again this 0th bit of multiplier will load. So basically if this addition has been performed, then only we will write that into this product register, otherwise we will not write. Okay, so after this first state, what we will do, we will shift the multiplier by right. So when we are shifting the multiplier by right, what we are doing is we are dropping the 0th bit, and first bit will become 0th bit. And similarly this multiplicand would be shifted in the left direction. So initially let's say it was 32 bit, now it will become 33 bits. So these 33 bits would be added to the product register, which is also initially because of 32-bit sum, so it would be 32. Now 32 bits would be added to 33 bits, it will become 34 bits. So similarly in the next cycle or in the next state, this multiplicand would be further shifted. So instead of 33 bits, it will become 34 bits. So similarly this will keep on happening for 32 cycles, and by the end we will have a result which is product of 64 output of 64 bits, and would be done. So what we have to notice here, that this load would be 1 only if multiplier 0th bit is 1. The other, this we are calling it ALU, arithmetic logic unit, because we can assume that for sake of simplicity it can perform addition, subtraction and other things also. So but even for non-generic case, it could be a 64-bit addition also. Okay, so this SL and SR will always be 1 during all the 32 states. After 32 states, SL as well as SR will become 0, so that no further operation would happen. Similarly, load will also become 0, so that my final product is there, it's going to be there, that's it. So yeah, so one acknowledgement that these figures are, or basically this whole explanation is taken from a book of computer organization by Hennessy Patterson, if somebody would like to see. So otherwise book of Roth also explains almost the same thing, so that explanation is equally valid. So I find this as more simpler way to explain, so I prefer to use Hennessy Patterson method of multiplication for explanation. So now one more thing, that let us say can we make this thing little better, little faster, or not faster, sorry, but it more optimized. So what you will observe here, that in the initial half in the first cycle, you will see that the left half of this multiplicand is empty, it's 0. And similarly this initially for the 0th cycle, this initial 32 bits are all empty, so they are not used. So can we somehow utilize this, and can we do something better? So if we try to see the optimized operation, so what can be done is that we can take a 64-bit product register or the output register. So in the 64-bit we keep our multiplier in the lower half, and the upper half we initialize to 0. So that's our product. So we initialize the upper half to 0 and lower half we keep as a multiplier. Now multiplicand is always 32 bit. So now we can simplify the whole process, because every time whenever we are shifting in the right direction, one bit we get a space of 1 bit here. And if you observe during the partial additions of a multiplier, you will see essentially 32 bits are being generated. That's it. Okay, so every time we are going to add 32 bits, a 0th bit, for example, after first addition will never be altered. So when it is shifted right, then it can take a space in this multiplier domain, and similarly after one shift right, this 0th bit will go away. So this particular method of addition will ensure that there is always a space. There is this both multiplier and our product can be stored in the same register, and both the operations are also same, and this also reduces the size of my my adder. So my addition would be only 32 bit instead of 64 bit. So this not only reduce the one additional register which we are using for multiplier, and it also reduces the delay, because instead of 64 bit addition we are now doing only 32 bit addition. Rest of the design is same. So rest of the design is same means my control FSM is still same. We are always doing the right operation. There is no left operation required in the multiplicand, because we are always doing the keeping the same 32 bit of the multiplicand. This add would again depend on the 0th bit of this product register. So this way it could be more optimized, and this product 0 would help us in deciding whether to add or whether to write to this product register or not, and rest everything is same. So whenever we are doing addition, we are only taking the upper half, or basically upper 32 bits of this and would be added to the multiplicand if product 0th bit of the product is 1. Okay, so and control is similar to our previous example. It's a 32 modulo 32 counter. Now as a conclusion, what we can see that this particular addition will consume 32 cycles to perform one multiplication, if multiplication is a 32 bit multiplication. So 32 cycles would be required, and one cycle would be equal to the delay of one 32 bit addition plus setup time and propagation time of a register. And total area requirement would be, we can say that this 64 bit register, this 32 bit register, and these two are the register requirements. Now these register requirements we can say would be there, because whenever we are multiplying two numbers, we would be storing the results in a register, and the input we are also expecting from some register. So we can say this requirement could anyway be there whenever we are doing multiplication, but for the sake of writing, for sake of completeness, we have written that these two registers are the requirement. In addition, we'll have 32 bit adder, and control is simple. We only require a modulo 32 counter or a 5 bit counter. So what would be the advantage over the other multiplier? So this multiplier is definitely very less in terms of area, and the hardware is also, or the connections are also quite simple. The state machine is a straightforward 32 modulo 32 counter, and where every time we are going to shift right, so there is no multiplexers involved, there is no other logic involved. We are going to write only if product 0 is 1, then only this addition would be written. Yeah. So that way this multiplier is quite simplistic, although it takes 32 cycles. So could be utilized when latency is not an issue. One more thing to point out here that this particular multiplication cannot be pipelined because this addition is used almost in every cycle. Because it is used in every cycle, this product register is used in every cycle, multiplicand is used in every cycle, so there is no other optimization other than this. So pipelining optimization can also be possible, can only be possible whenever resources are free and when you have some, for example here we have at least utilize these resources. Product register has been multiplexed, it is doing both the operations, it is keeping the multiplier as well as keeping the result. So this way we are trying to have some optimization. Okay, so with this motivation in mind, let's look at the other design also, how a division would be done.